Hello everyone, thank you for joining me for this next module in the Data Science for Material Science and Engineering workshop. My name is Zachary McClure. I am a PhD candidate in Professor Alejandro Strachan's research group in the Materials Engineering Department at Purdue University. This is one module in a multi-module part series where today the focus will be data querying, organization, and filtering. This lecture, which is one piece in this module, will be an introduction to data repositories and APIs, or application programming interfaces. Following this lecture, we will go through hands-on tutorials using NanoHub, as well as some homework assignments to solidify and drive home the tools and techniques that we go over today. So by the end of this lecture, we hope that you'll have an understanding about querying and data repositories, what they are, where they come from, and how to get their data, how to manage data through a library called Pandas. This library will offer you tools for parsing, logic operations, visualization, and type management for different sets of data. At the end of this lecture, we also hope that you'll be able to perform your own tailored queries specific to your user application, not just for the examples that we showed today. To understand these lectures, a basic understanding of Python programming will be needed. However, I encourage you that if you do feel like you're falling behind, we offer educational opportunities for Intro to Python on NanoHub, and the code that I'll be showing you today is available already on NanoHub through the tool MatData repo. So if you'd want to watch this lecture at a little bit of a slower pace, go through the code, line by line on your own, I highly encourage you to do that. I really feel that's the best way to learn some of these tricks. Okay, so before we get too deep into the API side of things, let's start with a brief overview of data science and machine learning in science and engineering. So we're at this really interesting paradigm in our field now where the data that we've acquired and the data we've begun to accumulate as a field continues to grow. And there's this push to really learn from data, from these large data sets in a high-dimensional space. So what this usually starts with, is the acquisition and handling of data. We get data from databases or collecting from high-throughput DFT. But we have this data and we want to now do something with it. So we build sets of descriptors or features for this data, and we can now use predictive models to say, okay, now with this data, what does something extrapolated look like or interpolated? And this is usually referred to as supervised learning. So these could be techniques like linear regression or neural networks. In addition to this module, where we're teaching you about data querying, there will be other modules offered in this series for things like predictive models, including supervised learning and linear regression, unsupervised learning, like pattern recognition. And once we have all these tools and tricks together, we can start to create a design of experiments. And in another module that I encourage you to participate in, we'll learn about a tool called active learning, where we take existing data, we create predictive models, and then we run experiments, or we do some type of a query. And we ask ourselves, is this the answer that we're looking for? If no, we improve our model and we create a loop. And at some point this loop will break and we'll go out with our best answer. Now, at the end of the day, we need something to hold all these things together. We need the data, the models, all of it to be held together by a glue. And that's where cyber infrastructure comes into play. Listed here on the right is not a comprehensive list, but a few of the major players in the push for cyber infrastructure platforms, where we can now create areas where our data, different types of data, are centralized, and users can access them through something called an API. Through a rapid query, we can create these data sets, build predictive models, and then go through this design of experiments loop. Alright, so today's focus is going to be the acquisition and handling of said data. So let's begin. So we first have to start and we have to ask ourselves the question, how do we get data? Where is it? What do we do with it? Well, it usually starts with the individual. An individual researcher goes into the lab, they have a machine, they gather data, they analyze the data, and they may or may not publish it. Perhaps they have a collaborator, and the collaborator has a different machine, or they have data that researcher A may not be privy to. Okay, that's good. Well, we have one pipeline here for researcher A and researcher B. Well, now we can also extract results from publications. So this requires a literature search, but this still relies on researcher A creating a pipeline to each of those papers, searching for the right papers, finding the right papers, making sure they have the right journal access to find said paper. So there's got to be a better way that we can do this though, right? It doesn't need to just fall on the user to find individual papers or have the right colleagues. So what if we were able to accelerate this innovation? How can we create something different for not only publishing our data, but consuming data, so that we can make sure that we have the best representation of what's out there? And that's where these open repositories come into play. These cyber infrastructure platforms where communities of researchers can upload and publish their data for other people to use. And with this, they can begin to share all their results. And when I say all their results, I really mean all of their results. Far too often, the data that we see published or the data that we show others is highly skewed to the data that worked. Let me say that again. The data that is published, the data that we show, is highly skewed to the data that worked or the data that we feel best represents the work. There are thousands and thousands and thousands of perfectly good experiments that don't yield promising data that we just throw away. And then someone else comes by 5 years later and they're going to do the exact same work. And you might develop a machine learning model and it doesn't have that data, and your machine learning model tells you that you need to go do all those experiments that somebody failed at 5 years ago. And so we're just spinning in circles here. So with the data that we have, we can learn so much from the data that works. But the data that doesn't work, the things that give us the wrong answer, tell us what not to do. And both humans and machine learning models can benefit greatly from knowing what works and what doesn't work. Now this creates an incredibly large amount of data, and so we need to rely on some type of cyber infrastructure to be able to query and analyze these large data sets. But once we have them, we can really leverage machine learning to really learn from our data and create high fidelity models to push ourselves into a new space. And that becomes very exciting. So let's again go through this process of data acquisition. So how do we now interact with these data repositories? So we're still researcher A interacting with the pipeline to the repository, but now we have a front end to work with. So that's option one. I could go to the materials project, which is a DFT database, and I could say, well, I want to know a little bit about chromia. So I could click on CR and O, and I can do some filtering for band gaps or formation energies, but it's going to give me a list of elements or compounds that contain those elements. But materials project is great, but it's a DFT database. Let's say I want to know something about the melting temperature. I could go to something like Wolfram Alpha, and I can just do a quick query of melting point of CR203, and I'll get some results back. And so what we'll find is that different platforms are going to be able to give us different leveraging abilities for different types of data. Well, let's go through an example with the materials project. So let's start with a web front-end example where we want to search for MgO, just basic magnesium oxide. So we'll search for Mg and O, we'll hit search, and it'll create a list of different compounds for us with a set of different properties. So I want to select this first one. It has a space group that looks familiar to me. This E above hull is a stability criterion parameter for DFT calculations. Just think that if it's 0, it's the most stable crystal structure. So you'll notice that these MgO compounds have a couple different crystal structures associated with them, but they're not the most stable. Now, this is not to say that they're not useful, but I want to go for just the most stable here. So I'm going to click on that selection, and now I'm going to be brought to this page for MgO, where I have a unique material ID, I have a DOI reference for how the simulation was done, and I have formation energy, densities, space groups, a lot of really good information here. And so the information that I've been able to show you here, it's very quick. It's really easy to get to it. It's very easy and intuitive to use this front-end user interface. But let's say I didn't just want to look for MgO. I want to look for, thousands of oxides or a few hundred. This would take days to go through the web front end and look for all those different oxide compounds. So it begs the question, well, if I'm able to get this result from the database so quickly, I had to click some buttons, but it's still instantaneous. What's going on between the front end and the back end that allows me to do this? And what it comes down to is this thing called an application programming interface, or an API. So all these databases, what unites them is a collection of data in a server somewhere. Maybe in a MongoDB format, some other format, and you, the beginning user, want that data. You don't really care how it's formatted, you just want to know what the crystal structure is. So you'll go to the web application and you'll ask the database, give me the crystal structure. But there's something that has to happen there first. Well, the web application has to essentially say, database, I want the crystal structure, and the way that it's translated is through that API, through a handshake protocol of sorts, where the web application makes a request from the beginning user, the API shakes on it and translates it over to the database and then returns the value. So that's great, but let's say we want to kind of skip out this web application step. I don't want to have to go through and click those buttons every single time. I just want to talk directly to the API, cut out the middleman. Well, we can do that. We can become an advanced user and we can talk directly to the API and get our results. So let's do an example of that now, where we're going to look for MGO again, but now we're going to focus on the example of APIs, which is the focus of this lecture. So doing a simple line of code, I can create my data by querying for MGO with a certain list of properties that I'm interested in. I can run this cell in my Jupyter notebook, and within seconds, I'm going to be returned a dictionary with a whole bunch of values that aren't very pleasing to look at compared to what I have on the right, but I have all this data on the right contained in this nugget of data here. So I have the task ID MP1265, I've got that. I've got my E above whole is 0, yep, I've got that. My volume is cut off, but there's a 19.27, okay, that looks pretty good. So again, we did this in seconds rather than the whole step-by-step process. So now what if I want to do this for, I don't know, let's say every oxide that exists in the materials project? We just have to tweak a little bit of code in that one line, where instead of saying query for MGO, I want to query for anything that has an oxygen atom in it, and I want to make sure that there are at least 2 elements in every single compound. So oxygen plus Mg, oxygen plus sodium, oxygen plus whatever. And I'll find that there are 62,000 compounds on the materials project, which is an enormous number. And we were able to do this in seconds. This would have taken years if we were to go through the whole GUI front end of the web application. We've done this in seconds now. We get the same sets of data as we did before. And now we can start to do things where we take our data and we can create large-scale visualizations with different sets of data, different coloring operations. And now with this giant data set that we are working with, we can start to find correlations and trends between different material properties very, very quickly. So now that we have the data, how do we store it? How do we manage it? So I'm sure all of you are familiar with CSV files. They're simple. They're great for storage. You've probably used them in Excel or other types of programming software. But that's really it. They're just good for storing the data, and then you need to import it with something. So let's say you import it with a NumPy array. Now, NumPy arrays are fine. They're great for math operations. It can get a little tricky if you're trying to index. You just need to be careful. But if you're trying to plot things with NumPy arrays, it can get a little confusing because you might have an m by n array, and you're thinking, okay, well, I want to plot the 3rd and 5th column to this index, and it can be very laborious. So maybe you're more of a MATLAB person. Maybe you've got a very large data set and you just want to do some matrix operations and be really sleek with it. That's all fine and dandy, but what if we had something that kind of couples, high functionality with efficient built-in libraries, the storage of CSV files, the operations of NumPy arrays? Well, what it boils down to is this really incredible library called Pandas, where you have all the functionality of sorting, parsing, editing, storage of data, management of data, but all with the functionality of something that looks very much like Excel, but in a Jupyter notebook. So we have these column headers where no longer do I have to say from a NumPy array, plot the 3rd and 8th column. I can just say, plot the density, plot the volume, or plot the volume, plot the IPF. And these are all very easy parameters to look at now. And it's an easy way to look at your data in a Jupyter notebook and figure out, okay, these are the values that I actually want to look at. So let's go through some examples of our initial query and then things that we can do to the data to get it into a more meaningful format. So the first thing that we can do is a dictionary to data frame conversion. Materials Project operates on a Mongo database format, so everything spat back to you will be a dictionary. Dictionaries are great for data storage. They're pretty efficient when you're trying to do a lot of operations, but they're not very visually appealing. So in one line, we can convert this whole dictionary into a data frame where all the keys become our column heads and all the values now become our rows. And that becomes a little bit more easy to visualize. We can remove data based on logic operations. So let's say we wanted to look for, very, very stable structures close to that E above whole equals 0. So I'm going to take my data frame, I'm going to look for that E above whole parameter, and if there's anything that's less than or equal to some cutoff parameter that I specify, I'm just going to push it to a new data frame. I want to filter everything out and keep it clean. Well, on the subject of keeping things clean, maybe I have a lot of data points where there isn't data. There's just gaps in some of the columns. And so what we'll find is that from our initial 60,000 query, about 10,000 of them meet the previous filtering for that energy criteria. Of those 10,000, about 900 have had the elastic tensor calculated for that crystal structure. So we have 9,000 compounds that don't have data in one of the columns. So I want to get rid of all of those entries. So if there's anything in this subset that doesn't have a number or it doesn't have data entered, in one line I can just drop all of those rows from the data frame. And now my data frame is a lot more condensed and meaningful with data that correlates because I don't have gaps in certain areas. So now that I have that data, I can start to do really powerful things like logic operations. So instead of trying to plot, the fourth column or the fifth column, I can just plot the density and the IPF. But let's say I wanted to plot a very specific compound and color it differently. I don't really know where alumina is in the data frame, but I know the properties of alumina that I'm really looking for, and I can use logic operations to find them in the data frame. So for my X component for the density, I want to look at my data frame, and I want to make sure that the formula equals Al2O3, and I want to make sure that it's the most stable structure, that this E above whole equals 0. Once these criteria have been met, I want you to locate the value of the density. And I can do the same thing for all these different compounds. So instead of having to search by hand through a data frame that could be 800 or 10,000 rows, this does it for me. And this plots very, very rapidly. Another thing that we can do is append existing data. So as you query your data, you might do some calculations, you might build on some descriptors, some features for your models. You can always append that data again with a single line, where you just create a new column in your data frame with whatever title you want, and you just append the array. Now the array obviously has to be the same size as the thing you're appending it to, but the operation is very, very simple. So with querying databases, we now have a leverage. We have a very bright opportunity to look at, say, a couple different ones. So as an example, Materials Project, Citrine Informatics, and Wolfram Alpha are three very different databases that offer three very different sets of information. What unites them all, though, is that they each have an API that can be used to rapidly query different sets of material properties. And then we can create really interesting visualizations like this, where let's say I want to look at an oxide property relative to a diamond substrate. So I can get coefficient of thermal expansion values from Citrine. I can get shear modulus values, bulk modulus values from the Materials Project. And I can get melting point properties from Wolfram Alpha. Now, these X's are going to be values that I queried from Wolfram Alpha, but because I have a lot of data now and I can leverage different types of material properties, what you see here in an open circle are actually machine learning predicted melting points and machine learning CTE values. So I've leveraged three different databases here to create this kind of Pareto front where I want to look at something that has a pretty low delta CTE and a pretty low delta shear bulk modulus. and a pretty warm melting temperature color. So something like this or this are probably going to be my happy compounds for material selection. Another exercise that we can do is looking at something like the density or ionic packing fraction with respect to the melting point, looking at a couple common oxides, and then asking ourselves, well, for these red dots, those are elements that contain, compounds that contain things like niobium, tantalum, tungsten, refractory type elements. So maybe I'm trying to search for an oxide that has a refractory type element in it for a certain application. And what we'll see is that there are a lot of these red dots that compete or are very, very close to state-of-the-art oxides like alumina and chromia. So through this acquisition of data and filtering, parsing, processing, I can begin to make material selection decisions very, very rapidly and well informed from a large set of data. So to summarize, what these databases offer is a way to access data not only for initial searches, but also for creating descriptors for machine learning models. And these descriptors and how we build these models will be the focus of upcoming modules, but now hopefully you have the tools to prepare yourself on how to create those descriptors and use them. Well, once we have these descriptors, once we have this data, we can easily append data, massage it, manage it using these Pandas data frames. And all the code that you've seen today is available in the link shown below at nanohub.org/tools/matdatarepo, and it can be easily modified for any need that you have, not just these simple queries that we did for a set of oxides. So moving forward, now that we've sort of concluded on this set of the lecture, I'd like to encourage you to participate in the hands-on tutorial where you'll actually run the tool, matdatarepo. You'll go through a couple of examples and you'll learn how to do the queries yourself. Then, following the hands-on tutorial will be a homework assignment to reinforce these concepts, and you'll have to make some additional modifications to the code to really get an understanding for what it's doing on both the front end and the back end. With that, I'd like to say thank you for joining me in this lecture, and I would happily encourage you to consider the other modules that we are offering in this workshop series. So with that, thank you, and have a good day.